So basically, this cooling tower is in installed for your air cooled system or water cooled system. I'm asking air cooled system or water cooled system.
Water cooled system.
Exactly, for water cooled system for heat rejection purpose. Okay, so this cooling tower can be your different types. Like firstly, for a major classification, it is divided into two, like a natural draft or a mechanical draft. So this mechanical draft uh, are basically used in our HVAC industry, not this natural draft. These are basically used in your utility power stations. Now, which are used in the HVAC, we have counterflow induced draft, counterflow forced draft, and cross flow induced draft. So this will have some terms and terminology. What is this counter? What is this induced force? So this all this I'll discuss. What is the difference in between these? All I'll discuss in the next slide. But before this, I'll just cover the working of this cooling tower. Okay, then I'll discuss this one because it will be easy to understand this one. So firstly, I'll cover the working of your cooling tower. So basically, this cooling tower uh, will have one inlet, okay, and one outlet. Okay, this is the outlet, and from this inlet, okay, the water is coming from your chiller. Okay, the water is coming from the chiller, and this is going to the chiller. This is your outlet. Okay, next. So when the water which is at say 95 degree Fahrenheit, which is a standard temperature that we used to maintain, 95 degree Fahrenheit inlet temperature cooling tower, and it is gone through this header. This is your header which rotates on its own axis. Okay, basically on this header now we have some sprinklers. These are the nozzles, or you can say nozzle or a sprinkler. Okay, so when the water from the chiller at 95 degree Fahrenheit enters to this header, this is distributed among these sprinklers. Okay, now from the sprinkler the hot water is splashes on this PVC filling. Okay, फैल जाता है पूरा उस पे PVC filling. So PVC filling like equal as जैसे मधुमक्खी का छत्ता होता है वैसा होता है PVC filling. Okay, एक दिखाऊंगा मैं आपको, शो करूंगा अभी, just 1 minute. So जब when water falls on this PVC fillings, the surface area of the water increases. The surface area of the water increases. So when the surface area of the water increases, heat transfer rate increase. So greater the surface area, greater will be the heat transfer. Okay. So after this, you see this is the mesh. Okay, wire mesh. The purpose of this wire mesh is for the introduction for air inlet. Okay, to inlet there, because you see in this whole cooling tower equipment, what are the components we have? We have one fan, okay, one header, sprinklers, PVC fillings, and your makeup water arrangement. So makeup water arrangement. This is your blow down operation process. This will show you why we require this one. And this is your sump, in which the water after the heat rejection will be accumulated. Okay, now how the water get cooled, how the heat rejection take place, this is the question. How the heat rejection take place? Now when the water splashes on this PVC fillings, the surface area of the water increases, and see when when the water is on this PVC filling, the fan is running. Okay, and this is a backward curve fan. Backward curve means this water air will flow at the back direction. Okay, so when it is running, it will suck the air from this side. Okay, it will suck the air from this side because this is open wire mesh. So when the air passes through this passage and when it comes in contact with the PVC fillings, the water and the air, which is at normal temperature, comes in contact, and when they comes in contact, heat transfer take place from the water to the air. So in this way the water get cooled and the air becomes hot. Okay, and the hot water goes out, hot air sorry goes out through this top header of the cooling tower. Okay, now one thing you see, this is one eliminator we have, eliminator. So eliminator is what? Eliminator is this week sometimes to call as a drift eliminator. Okay, drift. Why this is required? See, when the water when the air is blowing across this top of this cooling tower, this will have some amount of moisture inside this water vapors. So if you not install this eliminator, the water can go into the motor and the motor can jam. Okay, so just to, for the safety of the motor, an eliminator is required, so that only the air can flow across it, not the water. Okay, so this is the purpose of this eliminator. Now when the water becomes cooled, it settle down in the sump. This is your sump. Okay, this is your sump, and in this sump you will find three things. One is your makeup water, one is your overflow, and one is a bleed valve. Okay, so makeup water, you know that when, like for example, 100 liter of water is going inside this cooling tower, it is not necessary that 100 liter will come out. Why? Because there are some losses. Okay, what are the losses? The losses can be your evaporation loss. You can note it down, evaporation loss. Okay, and one can be your drift loss. Okay, drift loss, and second can be your uh, blow down loss. Blow down loss. Okay, this in detail will sorry, next para we have about the losses. No? For this calculation we have how much water will be evaporated, how much water will go into the drift, and how much will be used for the blow down operation. That all we see. Means calculation we have. Okay. So due to these losses, if the 100 liter of water is going inside
One,
the yes.
yes, one question. This when the water passes to the sprinkler from the inlet, the temperature will be 95 Fahrenheit, right?
Exactly.
Okay. Then when it reaches to the PVC filling,
Hmm.
what will the temperature will remain the same or it becomes ambient?
No, no. Actually, when it start sprinkling from this position, the surface area
Okay.
of the water increases. Surface area of the water,
Yes.
and when the surface
Yes.
area of the water increases, and when
Temperature
this
decrease.
air comes in contact with the water, the heat transfer take place from the water to the air. So in this way, the temperature of your water decreases. Okay, so here the heat transfer takes place and the temperature decreases. Okay, I think you understood.
Yeah, yeah. Okay.
Okay.
And this air inlets, both side, do we have nozzles in that or
No,
it
no,
will be
it
just
it is
opening?
just a nozzle. Just I'll show you. See, like this. This is an air inlet.
Ah,
Okay.
okay, okay, right.
Now, so water will accumulated into this sump. So we have three things here. One is your makeup water, bleed valve, and your overflow. So overflow, just to make sure that sump is full. Okay, makeup water to overcome these losses. Okay, because 100 liter is going, 100 is not coming, maybe coming 90 liter. So 10 liter will be provided by this makeup water just to complete the volume. Third thing is your bleed valve. Now there is a concept behind this bleed valve. See, the water which is going inside this header, this can be your hard water. Okay, hard water. Hard water means it will have calcium, magnesium carbonates. Calcium, magnesium, which increases the hardness of the water. Okay, so when the water uh, evaporated at this particular point, the hardness of calcium and magnesium settle down here in the sump. Okay, they will not evaporate, but the water evaporate and the hardness present inside that particular hard water, which is of calcium and magnesium, they will settle down here. Okay, so if we do not remove this calcium and magnesium hardness, the water will again day by day it will become hardened. Okay, if it has become hardened, it will leads to corrosion, erosion, and all. It will impede the heat transfer inside the coils and all. So it is important to remove this calcium and magnesium hardness. Okay, so how we are removing? There is a valve which is called as a bleed valve. Okay, so this bleed valve is used to remove this hardness. This valve is like just you can say like a magnet. Okay, so it just sucks all this calcium and magnesium hardness through this valve, and it is just rejected from this point. So with this hardness, some amount of water is also rejected. Okay, so this is also a blow down loss. Okay, so this is a function of this bleed valve, and the remaining water will go from this side to the back to the chiller. Okay, at what temperature? Which will be 85, because there is a temperature difference of 85 degrees Fahrenheit. Okay, now any question anyone have in this working of cooling tower, you can ask. Any question? Just if you understand, just let me know if that you understood.
This is a continuous process, right? Independent of any, I mean, they are everyone, every component is independently working.
Exactly, it will be working. If the chiller is working, this will be same, it will be working. If the chiller is working for 10 hours, this cooling tower will be working for 10 hours. Okay, so now next term what I want to discuss with you, this about the terminologies about the counter flow and cross flow and induced out of the forced draft. Now see, this is your cooling tower. Okay, and firstly I'll just show you that this is your counter flow and this is your cross flow. Okay, now in this cooling tower we have some uh, your PVC fillings, sprinklers, and this is your fan. Okay, hot water is coming here, cold water is going from this side. Now in this case, one thing you notice that the air we are taking from the bottom side. Okay, so it will go to this side up, and we are taking from this side and this go to this side up. Okay, and the water going to this down, means the water and the air are parallel. Air is going to the top and water is coming, sorry, air is water is coming top and air is going to the top. Okay, so there is a parallel combination of air and water. Okay, but if you see in this cross flow, the air is being taken from complete one side from the top to bottom. Now in this case the air will enter like this. Okay, and the water is coming perpendicular to the air. So air is like this side and the water is perpendicular to this air. Okay, so there is a mutual product. Now in this case the heat transfer will be better in this cross flow. If you ask me which one is efficient, cross flow or counter flow, cross flow is most efficient, more efficient than counter flow. And for higher capacities also we use for this cross flow, and for lower capacities we go with this counter flow. Okay, so this is the difference between cross flow and counter flow. Now next term is the induced and the forced draft. So induced draft is like you see in this case, the fan is located on the top. Okay, so if the fan is located on the top, it is an induced draft. If the fan is located on the bottom, means in the sump, okay, then it will be called as the forced draft. Okay, because forced draft why we are calling, because it will have to push the air to blow outside, means more work is required for this particular fan. Okay, so this is a forced draft if the fan is located on the bottom in the sump. If the fan is located on the top of this cooling tower, then it will be an induced draft. Okay, now For higher capacities, we go with this induced draft. For lower capacities, for medium capacities, induced forced draft is okay. For if you have a less space, okay, then forced draft is okay because induced draft requires more space. Now, one thing I'll ask you. Now, just look at this particular picture, and first question is: this is induced draft or it is a forced draft?
Mm, Actually, I didn't understood this induced and force.
Induced draft, like this fan is located on the top, so it is an induced draft. If the fan is located on the bottom, means in the sump, then it will be a forced draft. So this is the difference. Cross flow and counter
Oh,
flow, water air is taken from the bottom and it is parallel, then it will be a counter flow. And for cross flow means the air is perpendicular to the water, means taken from one side, and the water is perpendicular to this particular air. This will be a cross flow. Okay, so now now anyone tell what is the either it is induced or forced?
yeah, this is induced. Fan, it seems, is top side.
The fan is located on the top, it will be an induced draft. Okay, now next question is, it is a cross flow or a counter flow?
No, it is counterflow.
Counter flow means we are taking the air only from the bottom side, but in this case we are taking from one side completely, na? See,
Mm.
in this case the water is taken
Cross.
from one side completely.
Okay,
So
okay.
this will be your cross flow induced draft cooling tower. Okay, I think all of you understood now. Okay, now some parameters are there to just for the selection of cooling tower are required some parameters. First is your range. Okay, so range basically a difference between your cooling tower inlet temperature and cooling tower outlet temperature. Okay, so the difference between these two temperatures is called the range. So mostly we used to maintain 95 and 85 as the temperature difference of inlet and outlet. So 10 degree mostly the range is for cooling towers. Approach: difference between cooling tower outlet temperature and ambient wet bulb temperature. Okay, outlet temperature, it can be your outlet temperature, how much it will be 85 minus wet bulb. If I ask for New Delhi, I think it will be 63 thing. Okay, whatever the wet bulb. So if you subtract this value, you get the approach for the cooling tower. Evaporation loss. Now see, I told you that there are three losses: evaporation loss, blowdown loss, and drift loss. Okay, so when in this cooling tower, you have to do two things. One is to calculate the capacity of the cooling tower, one thing. Second thing is to calculate the sump or this makeup water tank capacity. Makeup water tank capacity. So to know this makeup water tank capacity, you must know that how much water is lost. Okay, so for the quantity of water which is being lost, we have these formulas: evaporation loss formula, blowdown loss formula, and drift range. Drift, what is drift? Drift, like with the water which is gone with the air in the form of moisture, that is what the drift. Okay, some water gets splashes outside this meshes, no, sometimes, so that will be a drift loss. So evaporation loss, we have this formula: 0.00085 into 1.8. Circulation rate means you have to convert GPM into circulation rate, meter cube per hour, into entering water temperature minus leaving water temperature. So this is the formula for evaporation loss. Cycle of concentration. Cycle of concentration, basically a term which is used by your water treatment people. Okay, some water treatment plants, some in big projects we used to have some water treatment room when the water is so much hard. In that case, treatment is also needed for the water. So cycle of concentration is basically a ratio of dissolved solid in circulating water to dissolved solid in makeup water. Okay, so solid means whatever the solution they are using for the treatment. Okay, so this, you don't worry about this one. This will be given by your water treatment people. Okay, this you don't have to calculate. You will get the value from that particular from the architect or from the treatment people. You'll get this value. Blowdown loss. So if the water, so this I already make you understood. If the water is quite hard, the salts of the water which is evaporated accumulated in the remaining water, thus increasing the concentration of the salt. Therefore, it is necessary to bleed the water which is carrying this salt from the system. This amount of water is called blowdown loss. This I already make you understood. Now there is a formula to calculate this blowdown loss. Is blowdown loss is equal to evaporation loss divided by COC minus 1. Cycle of COC means cycle of concentration. Okay, so this you will get from the architect or the treatment people, and you will get the blowdown loss. Drift loss, it is the amount of water carried away by the cooling tower fan due to higher air velocity. Means in the form of moisture or water vapor, or the water is splashing outside the cooling tower. That will be a drift loss, and this you can calculate either by 0.006. Hello, now I'm audible now.
Yes, yes.
Okay, okay. So drift range we used to take 0.006 GPM per TR. Okay, one example we'll take, in that you will understand how to use this values and all. Okay, one example will take. So firstly, cooling tower capacity. Designing the cooling tower capacity. The temperature difference between the entering and leaving water of the cooling tower is referred to as the tower range, which I already told you. Range difference between the inlet and outlet temperature. Cooling tower load is in BTU per hour calculated by the formula Q is equal to mCp delta T, which is a standard formula from thermodynamics. You might have heard about this one. So m is in Libyan per minute, Cp is 1 BTU per Libyan Fahrenheit, and dt is your temperature difference. Okay, so with the help of this formula, you can easily calculate your cooling tower capacity. Okay, for example, just I'll take one example. This formula is Q is equal to m Cp delta T. This is the formula. No? So m from where you will get. So for the m, you know that one for open system, because cooling tower belongs to open system. Okay. So for open system, one TR is equal to how much GPM? Anyone tell? I already told you. One TR is equal to how much GPM for open system? No. One TR is equal to 2.4 GPM for closed system. And for open, how much? 3. I think all of you forgot this. For open system, it is 1 TR is equal to 3 GPM. Now, for example, we have a chiller of say 100 TR. So for 100 TR, what will be your value for GPM? It will be 100 into 3. 300 GPM it will be. Okay. Now just make it in the next one. Okay. So you have the value in 300. Cp is equal to 1. Delta T is 10. Delta T is equal to 10 because in Latin after it is 95 and 85. So 95 minus 85 it will be 10. Cp. Cp is equal to 1. Cp is equal to 1. And just you can input the formula and you will get the Q for the cooling tower. Okay. And this anyone having doubt, you can ask. Okay. Okay. Next, selection of cooling. Anyone asking some question? Okay. Cooling tower selection. Types of cooling tower depends on the capacity, space, noise consideration, and height. Okay, means how much space you have, how much height you have. That depends on your cooling tower selection.
Okay.
Forced draft are suitable for low height, either mostly induced draft is used. Means for if you are having a height constraint, then you can go with the forced draft. Otherwise, induced draft are mostly used. Circular cooling tower is suitable for, means this is your rectangular. Okay, in this case we don't have any space constraint. So if in the case if you have any space constraint, then you can go with the circular cooling tower for less space clearance between them. It is less. It's, cooling tower to cooling tower, the space clearance is less in the case of circular. Now to determine the capacity, you must have the ambient wet bulb temperature, that will get from the ISO standard approach. You can calculate because cooling tower inlet minus your wet bulb that I told you. Water flow rate per ton means 3 GPM per ton for open system. 3 GPM per TR. So these are the selection parameters for your cooling tower, and capacity will get from this Q is equal to MCP delta. Now make a water loss calculation is there. For example, one example we have, calculate make a water sum capacity in liters when entering water temperature is given and leaving water temperature is given. Entering water temperature is 96 and leaving water is 86. Location is New Delhi and plant capacity is how much? 150 TR. Assume cycle of concentration is equal to 3 and 1 meter cube per hour is equal to 4.402 GPM. So this water consumption will be equal to evaporation loss plus drift loss plus blowdown loss. Okay, so what we have to do, just we have this formula now. You can directly copy this formula and just will copy here. So this is the formula we have. Circulation rate is how much? Because 1, 2, 3, 3 variables are there. Na? Circulation rate in meter cube per hour. So anyone tell me how you will calculate the circulation rate from this question? We have a plant capacity of 150 TR. What will be the flow rate? Tell anyone?
No.
How much? How much?
No. Sorry, I don't know it.
Okay. Just no problem. This is 150 TR. Na? For 150 TR, 1 TR is equal to 3 GPM. So 150 into 3. How much GPM it is? 450. Now we'll convert this 450 in meter cube per hour. So 1 meter cube per hour is equal to 4.402 GPM. So we will divide this particular value to get the value in meter cube per hour. 4.402. 102 we are getting. Na? So 102 is the circulation rate. 102 Entering water temperature, you know how much? It is 96 and 86. Okay, so directly I'll input this value is equal to 0.00085 into 1.8 into circulation rate, which is equal to 102 into bracket start. Entering water temperature is 96, leaving water temperature is 86, 86 or 85, 86 or 96, okay, fine, and bracket close. How much it is? 1.5. So this will be your evaporation loss, okay, 1.5. And for drift loss, this 1.5 now, just 2 we have considered, no problem. Just maybe for capacity may be different for that one, okay, just don't go with this one. Drift loss, so for drift loss I told you, you can consider either this one, or as a standard we used to consider 0.002 GPM per TR, 0.002. So 0.002 per TR, then we'll multiply this 0.002 into 150, because 150 is the capacity. We are getting 0.3. Okay, this you can consider. And for blow down loss, once you are known with this evaporation loss, divide this by COC minus 1, and you will get the blow down loss. Okay, anyone having doubt, just so I'll just repeat this one, no problem. And this is a simple calculation, only you have to input the value.
Yes, please repeat it once.
Okay, so this evaporation loss you understood, and this we have this input these values only.
Yes, yes.
This is the formula. Circulation rate we have this one, entering minus leaving. Okay, this is your evaporation loss. Next, for what drift loss, I told you 0.02 into 150, because 0.002 is for 1 TR, so I multiply with the total TR, which is 150. Now blow down, what is the formula we have? Just we'll go with this one formula. Evaporation minus, divided by COC minus 1. Okay, so evaporation is how much? Is equal to, this is the evaporation divided by bracket start. COC is how much? COC is given as 3 minus 1, bracket close, and you can sum up this one. This is the total GPM you're getting for GPM or liter per minute, I think. Meter cube per hour, meter cube per hour, meter cube per hour. So this will be your what call makeup water tank capacity. Makeup.
Okay.
Now understood?
Yeah.
Oh, okay. So this is how you'll calculate the makeup water tank capacity. Only 3 elements are there: evaporation, drift loss, and blow down loss. Or there is a just a thumb rule that you can consider 3% of the total flow rate. Okay, like the total flow rate is how much? It is like if I calculate the total flow rate is 150 into 150 into 3, that is 450. 450 into 0.03, 13.5 GPM. You can consider. So there is a GPM value. This is just a thumb rule. As for detailed calculation, you can consider this. Okay. Any doubt? Anyone? Okay. Next we'll consider. Next we'll start. Next topic will continue tomorrow. Okay. Just go through with this one. And if you have any doubt, you can ask me tomorrow. Okay. Okay, all of you. Just I hand up.
Yeah. Sure.
Okay. Thank you.